the transaction pattern, keep your data safe, and your code clean. Hello and welcome to episode number 24 of the Unity Performance Task Force podcast. I'm your host Ruben from TheGameDev.Guru, and as usual, I'll kick things off with a question for you. Have you ever worked on a project where anyone could call SetPlayerLevel from anywhere in the code, and then one day you shipped a bug where players suddenly became level 99? Sounds familiar? If so, this episode is for you. Even with encapsulation, your code can be unsafe. Let me explain. You might have a player class with a public method called SetPlayerLevel. Sure, it's encapsulated, it's just one function that sets a variable. But here's the problem. Anyone can call SetPlayerLevel. Your producer, a junior developer, or even you on a bad day. The question is, who should be allowed to call SetPlayerLevel? In most games, there aren't many situations where you should set the player level. Maybe when you kill an NPC and gain experience, maybe when you create a character, maybe when you sync with the backend. That's it. But if you have a reference to the player class, you have access to SetPlayerLevel everywhere, even in the credit screen, where all you need is to display the player name. So even with encapsulation, this type of code is unsafe. We must be careful and make some type of whitelist, defining in advance who can call these dangerous functions. This is exactly where the transaction pattern helps. The transaction pattern is a pattern that helps you limit operations to a reduced set of carefully thought out transactions. Before, you could call SetPlayerLevel or SetPlayerName or SetPlayerExperience anywhere. After the transaction pattern, you disallow that. You protect the integrity of your data so it's not easily possible to mess up. Here's the main idea. Everyone can get a reference only to the read-only part of your class. You create an interface, let's call it iPlayer, that contains only read-only methods and properties. The player class implements iPlayer. Everyone in your code only has a reference to iPlayer, not player. Now you might ask, how do I set the level? Here's the key. The interface has an execute transaction function. This transaction is well thought out in advance, and in its implementation, it has write access. Let me walk you through an example. You have a player profile class with getLevel and setLevel. SetLevel has write access, dangerous. You define an interface, iPlayerProfile, that only allows getLevel and execute transaction. The player has a read-only reference to iPlayerProfile. It cannot call setLevel by itself. When you kill an NPC, you execute a transaction, let's call it PlayerLevelUp transaction. This transaction receives write mode access to player profile. Inside the transaction, you call setLevel, save locally, sync with the backend, and maybe increase gold. These operations happen together in sequence, atomically. Here's the beauty. Transactions have names. Not just increase level, but names that describe what happens and why. For example, player killed NPC transaction. This forces you to think strategically about data transformations. Let's see this in Unity. You have a player script that kills an NPC every frame. When you kill an NPC, you execute a player level up transaction. The transaction increases the player level and prints it. Now, if you want to introduce a backend, you need to send updates to the backend. In the transaction, you'd call backend.updatePlayerProfile. But how do you access the backend? You could do backend.instanceStat.singleton, but that's a hard reference. If you ever want to replace the backend with a mock backend, you're stuck, and you're violating the single responsibility principle. Instead of a hard reference, you keep a reference to the interface, iBackend. But how do you get that reference? You don't fetch it yourself. Someone gives it to you. That's the whole point. The transaction pattern enforces this. The transaction shouldn't care where the backend comes from. It just receives a reference to iBackend. This keeps your code safe, testable, and flexible. Now let's talk about benefits. First, your code is much safer. Only well-thought mechanisms have write access. These mechanisms are the transactions. Fewer points of failure mean fewer bugs. Second, transactions are atomic. Setting player level doesn't happen by itself. It happens with saving locally, syncing with the backend, and maybe increasing gold. Transactions let you define sequences, which makes your code predictable and reliable. Third, you can record transactions. If you want another layer of security, record every transaction in a log file. If the player level is wrong, check the log and see what happened. Fourth, you can describe transactions. Force programmers to specify why they're calling a transaction. For example, pass a string like killed an NPC as a description. This helps with debugging and code reviews. Now, performance. Be careful with allocations. If you kill one NPC per frame, you're allocating every frame. If allocations are 16 bytes every few minutes, that's fine. But if it's every frame, or if the allocation is bigger, you need the right tools to avoid allocations. How? Two ways. One, cache transactions in a static dictionary or list, basically pooling. Two, make transactions structs instead of classes and use generics to avoid boxing. Structs on the stack don't allocate, but when you pass them as an interface, they get boxed. To avoid boxing, use generics. Make the execute transaction function generic. Execute transaction.t where t iPlayer transaction. Then pass the struct directly. With generics, seek doesn't box and you get 0 allocations. But here's the thing, only optimize if you need to. If you execute a transaction every few minutes, don't obsess over allocations. Complexity adds cost. A junior programmer will ask, why are you using generics here? You'll have to explain. That takes time. Before you implement fancy solutions, ask yourself, do I really need this? In my experience, the transaction pattern is invaluable when you have sensitive data. For example, player profiles in multiplayer games. It helped me a lot in Diamond Dash. Backends were a big thing. The sequence was critical. To reduce iteration times, I recorded backend requests and responses in JSON. Then I tweaked them. I created a mock backend class that replayed those responses without calling the real backend. This let me develop features fast. For example, to test a tournament where a player scores more points, I didn't need 4 devices. I just mocked the backend responses. Suddenly, I didn't waste days playing with multiple devices. So, to sum up, the transaction pattern makes your code safer, atomic, and easier to debug. It forces you to think strategically about data transformations. Use it for critical data player profiles, leaderboards, multiplayer state. But don't overdo it. If you're changing the scale of a confetti effect, you don't need a transaction. It's just visuals. But for player data, absolutely. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time.